So as Mario said, I'm the co-head of the PAX group at VERIMAG. And I do mostly program analysis like abstract interpretation, things like algorithmics of verification. I'm not a security expert. So people told me, what are you talking about with this Meltdown attack? You have no credibility. I mean, you don't know, I mean, so I looked at what newspapers said about hackers, and apparently if you are a hacker and you're doing low-level attacks, you have to dress like that, you know, with a hoodie. So I decided to bring a hoodie to have more strict credibility with the talk. So, yes, I'm going to first talk about cache attacks. So, as most of you know, main memory, like a so-called DRAM, dynamic random access memory, is slow compared to the processor in modern computers. It has been like that for I think, something like 25 years. And the solution is cache memories. So a cache is a fast memory that's located closer to the processor and that stores recently accessed code and data. And I put quotes around recently accessed because it's more complicated than that. We have an expert on these kind of issues here, Claire Maiza, so you can ask her about what it actually means when they say recently accessed. So to give you an idea of the kind of speed gains that this brings, I did some very naive experiment on my laptop. So if I do 50 reads from memory at locations that are not close by, because if locations are sufficiently close by, several memory accesses are actually one big memory access. It costs 32 clock cycles on my laptop. But if the data is in the cache, if I flushed out the data from the cache before doing that, it cost me 270 clock cycles. So I mean, don't take this kind of measurements too precisely because it depends on the gazillion factors. But still, you see there's one order of magnitude of difference. And apparently in some kind of configurations, you have more difference than that between accesses in the cache and accesses outside of the cache. In modern machines, so in the simplest configuration, you have one level of cache, okay, between your main memory and your processor. But on modern machines, you have a whole hierarchy of cache, and you have all these complicated replacement policies. If you have several processors or several cores, you have things called cache coherence protocols. It is extremely complicated, okay? And now, here is a simple timing attack. So, okay, what am I doing here? I allocate a buffer. And actually, most of this buffer has absolutely no usefulness, just that I have two locations in this buffer that are interesting. The location at position 2000 and the location at position 4000. I mean, these numbers are very arbitrary. It's just that it doesn't work if they are too close by or they are too close to the edges. Okay? And first thing is that I flush these two locations out of the cache. And since I'm on Intel architecture laptop, there is actually a processor instruction that I'm allowed to execute to flush this data out of the cache. So I do that. And then after that, let's assume that this part of the program here is some kind of privileged part of the program. Okay? The rest of the program is something that I can decide to run, but there's another part of the program that accesses privileged information. So the privileged information is this secret. And okay, here the secret is 1, it could be 0. Okay? And depending on that secret, I read location at the first offset, that is 2000, or at the second offset, 4000. I'm not writing anything. I'm just reading. Okay? I don't do anything that has any kind of official consequence. I'm just reading from memory. Then after that, I read from these two memory locations, and I time precisely the time that it takes to read from these two locations. And what do I get? I get that to read from the first location, I need nearly 200 clock cycles. To read from the second location, I need only 30 clock cycles. What is the difference? It is because I access the second location from the privileged part of the code just before I run my attack. So I see that this location was accessed recently. I don't have to have any kind of official transmission of information between the two parts. I just need to see what locations were accessed by the privileged code. And I do that by timing my own accesses. Of course, this attack here that I showed seems pretty silly because I'm running everything, the privileged part and the non-privileged part, in the same memory area, so I could have simply read the secret directly. This is not exactly correct because I could be in something like a programming language that has some kind of, what do you call that? These programming languages that offer some kind of separation between untrusted programs and trusted programs, right? Like when you're running Java, you can sort of isolate part of your Java code from the rest. When you're downloading JavaScript programs from the web, I mean, not you, your web browser is downloading the programs and executing them. They are not the JavaScript program is not supposed to be accessing any arbitrary location inside the web browser, okay? It's supposed to access only a limited subset of the things inside the web browser. And since JavaScript is in practice dynamically compiled into native code, it's some way to get it to execute code on your untrusted code into the same memory domain on your machine as some kind of privileged information like passwords. So okay, this is not, it was not completely silly attack method. But you can actually do better. The thing is, again, this is more complicated than that, and ask Claire for the details. But these cache memories, they use the same location in the cache for several locations inside your main memory. And in fact, a given location inside your main memory can only go into a specific part of the cache. And this is for making the cache design simpler and more efficient. So you can see effects of accesses to the cache for different locations in memory, even locations that you're not supposed to be, that you have no access to, if you also have yourself your own memory locations that have to be mapped to the same area in the cache. Okay? You see? And so one way to use that is to see that some other program, by doing its memory accesses, evicts some of your own data from the cache. So you see, you have your own data. There is some other program. This other program makes a memory access. This memory access maps to the same cache location as some of your own data. So it will evict. I mean, the cache has no infinite memory, so at some point it must throw out some of the things that were already stored. The system, the processor, throws out some of your own data, and then you notice that it was thrown out. I mean, in the terminology, it's evicted. You notice that your own data was evicted from the cache because next time that you access it, you notice that the timing is larger. Okay? So this is a cache timing attack. And these kind of things were actually proposed for getting information about cryptography. So you have some kind of cryptographic primitives running somewhere in your system. And let's say that this is a cryptographic primitive that uses some kind of table of constants. Okay? So you have a secret key, you compute something from the secret key, some kind of offset in the table, and you read the table at this location. And because you have an attacker program running in parallel to the cryptographic code, maybe with a different user, and your attacker program precisely times accesses to its own memory that use the same locations in the cache as the table of constants. And by doing this timing, it will know at which offset the table was accessed. And if you do that sufficiently often, and maybe with different data being encrypted, apparently you can, with some cryptographic primitives, reverse the primitive and get the secret key. So I'm not an expert on cryptography, but there were papers published on that. By the way, so some journalists apparently believe that this kind of attacks, so this is called a side channel attack, because you're seeing some kind of side effects on timing or energy consumption or whatever, some kind of indirect effect of the action. So this is called a side channel. And the journalists apparently believe that it was the first time with Meltdown and Spectre that information links inside the hardware were used. But this is not the case. I mean, there were attacks on cryptographic primitives like that, dating from '96. Even before that, there were some attacks on with cache side channel from 2005. Okay, so it's not novelty. Another fun thing. So, in modern processors, you don't want to wait. So imagine that you're running this code. So this is a function that takes as a parameter a pointer to another function. Okay, f is a pointer to a function. And my function process will just call f with a parameter 10. Okay, so I'm doing something very simple here. I'm just taking a function as parameter, calling that function. This is not something extraordinary, because when you use an object-oriented language like C++, typically all the virtual methods are implemented as calls to function pointers. Okay? So this is something actually fairly common. I didn't do anything object-oriented to do the examples to make things simpler, but that's actually fairly common. And so if you look at the assembly code, you see at some point it loads this it has this parameter f in a register, and it says, I'm going to call the procedure at the address pointed to by the register. So somehow, in order to process this information, your processor would have to know to which the location to which the register points, which means that it must have computed this location, right? And it can be slow. I mean, if my register is loaded from memory and the memory is not in the cache, then it would have to wait for the memory to be fetched, and then it could process the call. And it would have to stop doing anything until it has done that. So modern processors don't do that. Instead, they implement, modern fast processors, like things like you find in laptops, servers, etc. I'm not talking about processors that are optimized for for being cheap and eating only little energy and so on, that you find in embedded systems. I'm talking in things like this kind of machines. They start executing speculatively. This means that if they have an idea of what the pointer points to, then they will try to execute the instructions pointing at the location that they think the pointer should point. Okay? This is fairly complicated when you think about it, because they will start executing the instruction, and when they notice that it was actually the right pointer, they make the good guess. They will commit the result of the instructions, if they notice that they made a wrong guess, they have to retract all the actions from these instructions. So think about the difficulty of that. And apparently on some generations of Intel processors, to give you an idea of the difficulty of all this, the processor apparently has in-flight, so they call in-flight instructions that have begun to be processed and they are not completely processed yet. It is able to keep more than 100 instructions in flight. So you see the difficulty if you start having to retract some of that. Okay, so, oh, by the way, yes, in my process function, I'm not only calling f, I'm also timing the number of clock cycles that it takes to call f. And I'm printing the result. So now I'm just run a sequence of calls. So I call f0 and f1 are two functions that do exactly the same thing. And what they do is completely non-interesting. But they are different. They're not stored in the same location in memory. So when the processor starts executing speculatively one and notices that it is not the right one, it will have to retract what it has done. So I'm calling f0, f1, f0, f1, and then I'm calling a sequence of f0, and then I'm calling several times f1, and then I'm going back to calling f0. And you notice that when I start calling f0 after calling f1 the last time, it costs me more than 400 clock cycles. And then the timing goes down. Okay? Next time I'm calling f0, it goes to 300 something. And then if I call f1 instead, then again the timing jumps to nearly 500 clock cycles. But then the next time I'm calling f1, it costs only 300 something. Okay? And then if I go back to calling f0, again for nearly 500 clock cycles, and then it goes down. So the reason seems to be that the processor remembers the value of the pointer that I used last time in the process function, makes the guess that I'm passing the same value, and then if the guess is right, it's more efficient. If the guess is wrong, it has to retract, so it costs more clock cycles. Okay? So you see, one interesting aspect is that, okay, here I'm attacking my own procedure. This is not very funny. But if I was in a system in which there were in a language in which there were trusted and untrusted procedures and some kind of safety ensured by a type system, if I'm allowed to do precise timing, I'm allowed to see what some other function that I'm not supposed to have access to is calling. Okay? That's interesting. Also, something that is not very clear is that if you have several processes or several privilege levels, these kind of caches are actually shared between the processes. And for simplicity, what they use is some kind of subset of the bits of the instruction. So they store the addresses that you are supposed to, that it speculatively jumps to in an array in a kind of cache that only depends on parts of your bits. So you can observe actually what some jump instructions do in some other programs that are not in the same memory space as you, apparently. You see the fun part about that? Okay. Now, another interesting thing is branches. So if you were in an old processor, like 6800, 66000, which has a fairly decent processor at the time, there were documentation, and it told you how much time it took in clock cycles to process a jump that is taken and a jump that is not taken. So a jump, if you have never programmed in assembly, you see your code, and at some point it says branch if equal. And the branch may be taken if the things that you have compared are equal, and it's not taken if they're not equal. Okay? And in an old processor, it would first do the comparison and then perform the branch. But then you would have to wait until the comparison is done to perform the branch. Which means that if your comparison is made from values that have to be accessed from memory or computed using expensive instructions, then you would have to wait until these values are known and the comparison is performed in order to perform the branch. So again, they do speculative execution. In some early speculative execution, they did something fairly very simple. So for instance, I think it was some Spark processor. If you were branching backwards, they said, okay, branching backwards, it's probably some kind of loop, and the loop is likely to be taken more than to be exited. So they were speculatively executing the branch backward. But on more modern machines, they have some kind of prediction engine that looks at the past behavior of that branch and tries to predict what will be the future behavior. So I played a similar trick. I'm calling my process function with a flag that goes between 0 and 1. And you see, so the pattern is less clear here, because it goes to between values above 50, 60 to values around 40 clock cycles. And it seems that if I go from a sequence, I don't recall which one is the branch taken and which one is the branch not taken, but that never mind. If I go from a sequence of flag 0 to a sequence of flag 1, the first 2 times I'm running with flag 1 are expensive, then I go to less expensive execution, and then if I go back to flag equal to 0, again I jump to some more expensive execution for two times, and then I go back to less expensive execution. So it seems to me that they have some kind of buffer that, I mean, the previous one for the branch target apparently only cared at the last target. Apparently here they do something more, they try to do something more clever, like if once in a while you do they think there's some kind of common choice, most common choice, and then sometimes you do a branch in the other direction, and they don't want you branch in the other direction to pollute the general behavior. There's some kind of frequency voting systems, probably.
Okay,
Yeah?
it's a counter to bit. It's
Yeah.
a bit counter, but that's why.
Yeah. But still, we can use that. And again, these things are not necessary. They're not. You can observe behaviors of programs that are not supposed to be in the same security domain as your program, apparently, because they share the same predictor. So if you can properly align your own branch instruction with the instructions of the other program, you share the branch predictor location, and then you can observe what they do. So for instance, if the other program is a cryptographic primitive implemented naively, then you see? Okay? So for instance, if you know cryptography, you know there's a cryptographic primitive called in RSA that's fast modular exponentiation. The simplest way to implement fast modular exponentiation is with an if then else and a bit of the exponent. And if you do that with an if then else and a branch, and you can observe the branch predictor from another part of the code, then you can pretty much extract the key, apparently. That's funny. Okay, so again, all of this was known before there was those agitation about Meltdown and Spectre. There are papers written on that. I mean, some cryptographic primitive code has been hardened against this kind of attacks. So nowadays, they avoid doing this kind of branches in cryptographic code. And more generally, they try to have code that executes in constant time so that you're not able to observe timing effects on the cryptographic primitives. Again, I suppose that Jean-Guillaume knows things better than myself. Okay, so another fun thing. So KASLR. So does everybody know about virtual memory? Okay, so in systems, in big systems starting from the 70s and in personal computers starting from early 90s, the 386, I think, Intel 386. You have a system that is able to translate the memory locations that you see inside the program into physical memory locations inside the system. So when you were in a simple computer, personal computer, earlier computer, the addresses that you saw inside the program were pretty much the addresses that were sent to the memory chips, physical addresses. Here you have some kind of indirection, and this indirection enables the operating systems to implement protection. So if you knew the old, so for instance, if you are in the iMac building, in the ground floor there's an old Macintosh computer that I think ran on a 68,000 processor. And in this kind of system, all the programs run in the same memory space. So if you did something wrong inside your work processor, you could crash the operating system as well. Nowadays, each program runs in its own isolated memory space, and you cannot access the programs from the other users directly through memory. This is implemented. This is one effect of this virtual memory system. So when you see inside your program you have a pointer and you're accessing a logical address, it can map to physical memory, and there's a kind of function that tells which physical memory is actually used. It can map to physical memory, but this location is marked to be used only for people more privileged than you are. That means only for the operating system. So it can map to private addresses from the Linux or Mac OS X kernel, for instance. It can map to nothing, in which case, yes, sorry, there's a bug in the slide. This 6secv should be here. Okay, it can map to nothing. So, for instance, when you access a null pointer is supposed to map to nothing. And when you're trying to access privileged memory, or you're accessing memory that doesn't exist inside your process, the operating system, so your process is trapped, control is transferred to the operating system, and the operating system, if you're under a Unix system, sends you segmentation violation signal. So okay, if you don't catch this signal, your process is terminated, and the user sees some kind of warning message. You can catch this signal if you want. If you run Windows, I think it says votre programme a une erreur de segmentation, general protection, faute générale de protection. And say final case, this is memory that exists but that has been swapped out to the disk, and then the operating system has to fetch the memory from the disk. Okay? So, in order to make various kind of attacks more complicated, so many attacks, many security attacks are simpler if you know the addresses of code and data inside memory, if you are the attacker. But if you are the attacker and you're sending, suspicious things to somebody, you don't know exactly the system that that person is running, right? You're just sending things. So, if you actually know the precise version of operating system and precise version of the programs that that person is running, then you could actually know the virtual addresses of many things inside the program. In the past, it was like that. You compile the program, and the program always loaded certain things into the same virtual addresses. So if you were an attacker and you knew the versions of things, then you could send something that was crafted to exploit this knowledge about the addresses. So this was addressed by address space layout randomization. So nowadays, I think it's true on Linux, Windows, probably Mac OS X. When you're loading programs, at least assuming that they are compiled with the default settings and blah, 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 it randomizes many locations inside the program. So the first time that you load the program, the addresses are like that. Next time, the addresses are in some other configuration. So it's harder for the attackers because they have to make guesses, and if they guess wrong, then they crash something inside your system, and you're likely to notice. And it did that also for the operating system kernel. So nowadays, when you boot up a Linux kernel, it loads parts of the kernel at randomized addresses. So if you're trying to mount an attack on the kernel, you nowadays have to guess addresses. Yes, there's a side precaution, is that there was, for debugging and performance measurement purposes, you could know the addresses of the symbols inside the kernel by looking at a special file called /procs/KLSIMS. So nowadays, by default, all the addresses shown in this file are 0. And you have to make a special tuning to see the actual addresses. This is actually needed for some kind of performance and debugging purposes. Now, second interesting thing. So all of that was pretty reasonable, right? Now, another reasonable thing. As you all know, programming parallel systems is complicated. And you have to use logs and not forget about the logs, or you use atomic instructions, but atomic instructions are pretty limited in what they do. And something that was pretty much in vogue at Popol a number of years ago was to be able to program with transactional memory. So people were talking about transactional memory. And actually that was implemented in hardware. So in the modern Intel processor, including the one in that laptop, have hardware transactional memory. What does it mean? It means that I'm able to do things by transactions. A transaction is like a block of instructions that will be executed from the point of view of memory in one atomic thing. One atomic execution. I cannot have interleaving between my transaction and another transaction, or some other actions by other processor calls or some other processes. It seems very nifty, okay, for doing updates to some kind of shared data structure. And so it is implemented on modern Intel systems. So you can, of course, implement transactions by having a global lock on your memory, but of course, in terms of performance, this is horrible. So hardware transactions, they do things like they start to process the two transactions at the same time, and they notice if there is a conflict, otherwise it works. So there are interesting things that map to Intel instructions x begin, x end, x abort. Okay, you can also abort a transaction. And yet there is even a kind of higher level construct in GCC for writing transactions. So there is a transaction atomic, there is transaction relax, and so on. It would be even not quite as fun if actually this was in the official main GCC documentation, but it's in another documentation. But actually it exists, believe me. And so why am I talking about transactions here? So it seems like a very nifty feature. The thing is, if you do an access that would result in a trap, segmentation violation inside a transaction, I'm not quite sure why, and I don't know if it's official because I tried reading the Intel documentation and I didn't see where this was actually written that it should perform like that. But if there is a segmentation violation inside the transaction is retracted on your process, doesn't get a segmentation violation signal. So it doesn't do the hardware trap, it just fails, aborts the transaction. And this is what's interesting. So, here, what I just did was to read from various addresses inside the transaction and to time the transaction. So if I read from an address, of course I'm reading from addresses that are either do not exist, either are mapped to kernel memory. So in both cases I should get a segmentation violation. But I'm not getting a segmentation violation because I put this access inside a transaction that fails all the time. So I try various addresses. It always takes 210 or something clock cycle. And then there is a value that is significantly lower than all the other values. And if I check, this is actually the address where the kernel is loaded. So, I mean, this attack was published in 2016. And actually, if you just follow the ID inside the paper and you re-implement it yourself, it actually works. It's incredible. So KSLR is broken easily. Okay. Now Meltdown. As I said, speculative execution proceeds quickly. And modern processors, they speculatively continue executing all the time. If the execution was incorrect, they retract the architectural effects. So when they talk about processors, they divide things that they do between architectural and microarchitectural. Architectural are basically things that are documented inside the processor manual, which, by the way, for Intel processor is 4,500 page long. And so these effects that are documented are retracted. So if you load a value inside a register and your speculative execution is aborted, you don't see the load into the register in the rest of the code. But there are some microarchitectural effects, like timing, effects on timing and caches. And typically they are not retracted. So you can measure the effect of speculative executions because of the impact on timing of other things that are executed, or because they load things into the cache, and that you can measure. So now my own personal implementation of the Meltdown attack, because at the time when the Meltdown was made public, there was only a paper with no proof of concept implementation. So I tried following the IDs in the paper, and I saw do transaction, read a byte from kernel memory, so register R15 points to kernel memory. I read a byte and extract one bit from this byte, and depending on the offset of the value of that bit, I'm accessing my own personal array. So my own personal array is pointed by register R11, and I read from that buffer at the location depending on the bit that I've read from kernel memory. Okay? All of this is wrapped into a transaction. So if you follow the architectural description of the system, I begin a transaction, I'm reading from kernel memory, I'm getting a segmentation violation, and I don't know where this is documented, my transaction fails, or if it was not inside the transaction, I would get a segmentation violation. Okay? What happens is that the system reads from kernel memory, extracts my bit, so it speculatively extracts my bit, speculatively reads from my personal buffer, and then it probably kills my transaction at this point. Okay? So what's important is that I've read from my personal buffer from a value that is supposed to be in protected kernel memory. And then by just measuring the time that it takes for me to access two locations in that buffer corresponding to the two values of this bit, I can know if this bit was 0 or 1. Okay? So this is the Meltdown attack as documented in the paper, except that they didn't give very precise indication, very too detailed indication about source code, but it's pretty. You can do it if you see that. When I tried to do that, it worked on my laptop machine, but not on my desktop at VERIMAG. I found another exploit from GitHub that worked on both machines. One difference, so it doesn't use the same sequence of instruction that I'm using exactly. And for that other exploit, it does something like 300 useless additions before actually running the attack. And I try removing these 300 useless instructions, and it makes the attack less efficient. So probably you have to set up, you know, the pipeline inside of certain processors in a certain way to make the attack work. Okay. I can do without transactions. I have to catch the segmentation violation signal. It works. It's more complicated. And you can also extract values byte per byte instead of extracting them bit per bit. Okay? You have to distinguish between 256 memory locations. It's possible. Now, both my own implementation and the one here, they need to force, I'm only able to attack, and the other exploit is only able to attack kernel locations that have been loaded into the cache, probably loading into first level cache, so the cache closest to the processor. I believe this is because the level 1 cache is indexed by virtual addresses, not by physical addresses inside the Intel processors. Of course, none of that is documented officially. What actually that guy was doing, and I did the same. You see, I didn't understand why my attack was not working. So after spending hours on that, I downloaded this other attack and noticed that he was doing a system call just before doing the attack. So I made the same system call, and my attack started working as well. So essentially, you have to make a system call that loads certain parts of the kernel into the caches, and then you can attack this part of the kernel. And this kind of remarks about the L1 cache was also reflected by what's written in Google and Intel documents about Meltdown. So they talk about L1 cache. So you would think that it is not too scary because you have to be pretty lucky for interesting data to be precisely inside your L1 cache when you actually want to mount the attack. But you know, initially when you reading the reports, you could read anything in memory. And but then people were in a haste to update Linux kernels and Windows kernels, so I really didn't see why they were so in a hurry to update kernels to patch the Meltdown issue if it was only about L1 memory. It seemed weird. And there are rumors on Twitter by the groups that proposed that attack. So the group in the University of Graz in Austria, that it is possible to exploit some race conditions inside the processor to attack locations that are not in the cache. So I don't know exactly how, because some people say, why don't you prefetch locations into the cache? And I try doing that, but it doesn't work. But maybe you have to prefetch it into certain conditions, and then the memory is loading into the cache. I don't know. So probably there is something yet unpublished that is much more severe than what is already published. Otherwise, I don't explain all the agitation. Oh, what is the mitigation for that? So, as I said, kernel address space randomization was defeated by a very simple attack that even an incompetent newbie like myself can implement by reading the paper in about 1 hour. So, what they were proposing was a patch that essentially, when you run a user program, instead of mapping the kernel memory into the user program and marking the kernel pages as private only for kernel, doesn't even mention the kernel pages. So the problem here is that when you call in the kernel, you're making a system call, the kernel will have to change essentially the parameters of the virtual addressing system. Previously, it didn't have, if you were just doing a system call, executing the kernel and getting back to the same process, the kernel didn't have to change the setup of the virtual addresses. It was just using some addresses in private memory that you were not allowed to use. Here, it will have to change the basis of the virtual addresses, which, as far as I understand, entails a complete flush of the cache for the virtual addresses, which is fairly costly. I'm not an expert on Intel architecture. Maybe I'm wrong, but as far as I understand, it flushes all something called the translation weaker side buffer, which is some kind of cache that remembers some parts of the translation between virtual addresses and physical addresses. So it would be like a full context switch. And apparently, so some people are saying that it makes things 30% slower on the kind of workload, some even higher numbers, some lower numbers. It probably depends a lot on how many system calls you're doing. Okay, so this was some of the cache, the patches that were integrated. So by the way, this is why people were noticing that there was something wrong during the Christmas holidays, because usually changes to virtual memory inside Linux, they take a long time to be accepted, because if you do anything wrong at that level, it will have terrible consequences. And then people were saying, why are they accepting these things so quickly? There must be something fishy going on to explain that. Okay, so the Spectre attack. Let's say that I'm running a program inside, so I didn't implement the Spectre attack, okay? So assume that you're in a program that checks the size of arrays before you allowed, in a programming language that checks the sizes of arrays before you're allowed to access them. So internally, your language does something like that. It tests whether the index is within a bounds. If it's not, it raises an exception. Otherwise, it gives you the data. And then you're allowed to use the data inside your untrusted code. Okay. The attack is actually simple. You train the branch predictor into thinking that the else branch, that is the branch that accesses between the bounds, is more likely. And this is not hard. You're just accessing the array within legal bounds, okay? Several times. And then you flush all your personal buffer out of the cache, and then you execute an out-of-bound access. The branch predictor will say that let's try if the index is within the bounds. It accesses a location that should not have been read and writes into your own buffer at a location that depends on this data that you shouldn't have been able to read. Of course, the architectural effect of that will be retracted, but still some data from your own personal buffer will have been loaded into the cache, and then you can know which data was loaded into the cache by a timing attack. So you can sort of break out of a safe language like that. So the idea is, the novelty is not that you can leak information using caches, because that was already known, is that you can leak information from speculative executions, and you can even induce speculative executions on purpose. Okay? So once you say that, this seems like pretty obvious, but somebody had to think about it and actually make it work. And some other more scary things is that since part of the predictors, as I said, is shared between several programs, you can even induce speculative executions in other code. So you can train a branch target predictor or a branch predictor using your own user-level program in a certain way that will induce certain behaviors into some other program, including kernel code, apparently. I've not tried it. Okay, I could allow myself only a limited amount of coding and experiments, because I have more important things to do, like filling Excel sheets for the European Union. But apparently it's possible. you're not forced also to use the data cache as a way to exfiltrate things from your speculative executions. You can use also the branch predictors themselves to extract information. So there's a lot of funny, lots of funny configurations that you can use. Okay, so what are they suggesting in terms of mitigation? So for instance, in order to, you see that branch target prediction, if you are able to poison it, is pretty scary, because you can choose where the speculative execution will branch inside the other code, the code that you are attacking. So this is pretty scary, because in a large amount of code, you can more or less always find sequences of instructions that suit your purposes. So you can sort of make your processor jump in speculatively in arbitrary locations. So they're suggesting a way of mitigating that essentially breaks branch target prediction. So my understanding of what they do is that they purposefully do things that break the branch target prediction. So branch target prediction was an optimization for speed, and now they purposefully do things that will prevent it from operating properly. So this is a bit weird. So there is something, there's a patch on LLVM that introduces something called return trampoline. Red poline. Okay. Probably longer term things will be to be able to flush more microarchitectural cache state from the cache. Also, to stop speculative execution. So for instance, if you could stop the speculative execution after doing this test, then you would break the attack. So apparently Intel has started to document that certain instructions that do some forms of memory fences actually stop also speculative execution. So by inserting these instructions at appropriate location, you can stop some of this attack. And apparently there's a patch somewhere, I think Microsoft is trying to introduce a patch that if they see something like a pattern like that in code, like tests and accesses at a buffer depending that is supposed to be cut off because of the test, then they will introduce this kind of fence. People are talking about that, detecting these kind of patterns, and then breaking the processor efficiency purposefully on this kind of patterns. Okay, so conclusions. My first conclusion, things are starting to be too complicated. So let me give you another anecdote. Earlier, last year, so I had a brand new laptop, so this one, and when I was trying to install Coq, which is things to do proofs on programs, and the compilation of Coq was breaking. So I didn't understand why. I blame, maybe this is faulty memory chips, maybe this is a bug Coq is written in OCaml, so maybe this is a bug in OCaml, maybe this is a bug in Linux, maybe because it is because we buy laptops from Marché Public and they're not good, I don't know. But I had some random crashes. And it was later learned that there was a bug actually in the Skylake line of processors from Intel when you're using hyperthreading. So hyperthreading is a very scary feature of Intel processors in which the same core executes two different streams of instructions. So one single core behaves as two logical cores simultaneously. And of course this is extremely complicated. And there was something wrong in there that was triggered by some sequences of instruction, including one sequence of instruction inside the OCaml garbage collector, if this OCaml garbage collector was compiled with GCC -02, not with -0. Okay? So it depended also on your version of CAML, because the default setting for compiling the garbage collector changed over time and so on. Okay? And so this, as far as I understand, cost a lot of energy at people from Jane Street Capital that were running financial computations in OCaml. It also cost some time from the OCaml main designer Xavier Leroy from INRIA. And some months later, there was an erratum from Intel saying that they fixed some bugs in microcode, including some bug in hyperthreading that resulted in nonsense executions in some contexts, which was the thing that was breaking OCaml. So it seems to me that things are becoming too complicated. So executive summary: cache observation attacks are not new. Branch predictor observation attacks are not new. Attacks or side channel attacks during speculative execution, as far as I know, are new, but I'm not a security expert. It's funny because I read a paper for some years ago, a couple of years, in which they were talking about things, and they were talking about speculative executions having microarchitectural effects. So they were almost, I think they were talking about microarchitectural effects after a segmentation violation, but they didn't follow up doing an attack. Or maybe they did, but they didn't publish it. But because you see, they were almost there, these guys. And so as far as I know, these things are new. I mean, new in published literature. So, unknown. Is it possible to use Meltdown on data not in N1 cache due to race conditions? So there are some rumors on Twitter and probably some unpublished things. I don't know. Can you force loads into cache? What happens if you do a prefetched on a privileged address? I don't know. What do they do? What do they know that we don't know that justifies patching everything so quickly? When I say patching so quickly, apparently there are systems that no longer boot after they upgraded some kernels. Do you have questions? So, by the way, yes, gratuitous advertising. So this is the PAX group that does program analysis, things like polyhedra and coq, and verification and security. Okay, so you can ask me or you can ask Marie-Laure Potet for information about internships, thesis, things like that. But okay, do you have questions?
So you probably know about these Intel SGX, the secure enclave for execution. Do you know if any of these attacks can jump out of that also? Because it's supposed to run on the same chip, but with all separate memory and stuff. Well, not memory.
I tried. Okay, so since Christmas, I tried updating myself on the novelties of the Intel platform since last time that I read about the details of the Intel platform. So I saw these things about SGX and the enclaves. So for other people, this is a mechanism into some Intel processors that is supposed to enable a cloud provider to run code in other data provided by some client without the provider being able to read the data from the client. So this is something like some kind of transparent, cryptographic signing and so on, to prevent the operating system and the hypervisor and so on from reading the private data into the enclave. I don't know if you can attack that. I don't even understand actually the enclave system. I tried reading the Intel documentation and some papers on it, but
are there known and reported attacks that have been working with this?
You mean not proof of concepts,
Yeah,
but
not published paper, real attacks. On companies, on whatever.
no, not as far as I know. But okay, the idea is sufficiently simple. I mean, once you know the ID, you take and you know that you're only attacking one cache. Even a complete amateur like myself can implement it in not much amount of time. So if you then probably you have to spend a lot more energy, if it is possible, to use Meltdown against things not in the cache. Probably, if this is possible, if you spend enough time and enough people, experts on it, you will discover that. So, it was only discovered officially at Christmas. I mean, before that, because they wrote the paper. There's absolutely no reason to believe that nobody discovered that before. And didn't document it publicly. It's you cannot detect it, especially if you use the transaction system. It's very innocuous. So just to complement what I was saying about Intel doing things that are too complicated. So Intel, a couple of years ago, introduced some hardware feature for checking bounds of accesses to memory. And there are some bound buffers, and there's a whole cache system for bounds that I've not quite understood. And it is exploited by special options in GCC. You can compile, yes. There's an advanced bound checking system in GCC that exploits some hardware feature in the modern Intel processors. And then it was introduced in 2015. And then there are already some people in GCC that talk about deprecating that, because apparently nobody uses it, it's a loss in performance of what. So you see, Intel introduces things, and it's not even implemented in all compilers, and people start moving out of them. So my impression is that there's too much complication and going on. Any other question? You there?
Yes. There are some other bugs in Intel processor related to management engine.
Ah!
Is it connected or is it totally different?
Okay, so there is something totally insane. Previously, when you were running an Intel system, you were supposed to have your user programs at ring 3 of security. The operating system was at ring 0. But in some, so if you're running with virtual machines, like several virtual operating systems sharing the same machine, there is on top of that an hypervisor. So people started nicknaming the hypervisor ring -1. Then you are on an Intel platform, and since things were introduced for running on laptops and controlling fans on laptops, that is called system management mode, which uses special interrupts and special arrays in memory, and that completely circumvents what your operating system is doing. So some people nickname that ring -2. And then it was discovered that on some Intel platforms, they have actually a second processor, which is some kind of microcontroller or low power core. And apparently in some recent iterations of that system, it's actually running Minix. So Minix is a Unix-like operating system developed by a professor called Andrew Tannenbaum. Apparently, they're running that on that microcontroller, and it's called the management engine. It's supposed to be a kind of system for managing fleets of enterprise computers. So something that completely circumvents your operating system. So I've never used it myself, but apparently it's some kind of thing that is able to reboot remote machines, reinstall remote machines, and so on in an enterprise setting. And apparently there have been sequences of security holes in that management engine. So this is unrelated to the Meltdown attack. It's a different kind of holes created by Intel. Any other question?